Welcome back, and let's start with drag delta function. So when do we use such a function? If we want to put an input, let's say, to our complicated ordinary differential equation from the right hand side, we could use such a function. And in what kinds of situations we would need something like that? Let's say an airplane making a hard landing. So it's not a good day, but it's somehow hitting the ground with a little bit of more impact, or a mechanical system that you're hitting by a hammer blow, or let's say a ship hit by a single wave at one instant. You don't know maybe the gross amount of impact that you're putting into the system, but what you know is actually the momentum transfer. So if we could reach up to that point from some undefined quantities like a big crash, a big impact, and so on and so forth, something that I cannot quantify really, and it looks like infinite, I can um, put that into a form such that it would now represent a momentum transfer. Then I will be able to make some calculations out of it. So phenomena of impulsive nature can be, which are applied over very short intervals of time, and in that interval you don't know how much actually the impact's real energy is, but you can model this to a point that you would understand how much momentum is being transferred to your system at that point. So let's move with some definitions and insight to this function, and then we will do the Laplace transform of it, and we will look at one of the examples from your book. So let me move on to the handwritten notes. So we are talking about short impulses, a kind of a unit impulse function. So I want to find or develop, not find, develop a function such that it would represent a unit impulse function that might look something like this. But I want to, for my modeling purposes, I want to squeeze it to a tiny area, let's say around zero for now. And at zero, I want this delta x function. You could put f of x over here. It doesn't matter, just to make it separate from any other f of x. I want to put it as delta x because it's Drake's notation and it's historically nice. And it, at point zero, let's say this shoots all the way to infinity. I don't know where it stops, but out of any point zero, so it's so tiny that this thing happens just at zero. Okay, that's kind of my starting definition. And anywhere around zero, which is not zero, I have my function going to zero. So that's kind of what an impulse looks like in my modeling mind. Okay. Now we will define an integral that uses this function. So it goes from minus infinity to infinity. If I take my integral of my delta function, delta x by dx, that integral I want that integral to be 1. So I'm building this function, right? I have the ability to define anything. And that little tiny area underneath that infinite shooting peak, the area underneath that, I want that to be 1. So this is kind of my starting point for my modeling. And I will try to reach and solidify what's described in this quite abstract thing. The abstractness comes from this infinity. If something is going to infinity, how come the area underneath is 1? So let's have a look at that first. Let's define our function as 1 over 2 taus. Okay, so let's put a line in my normal Cartesian coordinates, and let's define this thing from minus tau to plus tau. This is called the Dirac function. Not the Dirac delta function yet, but the Dirac function. Now, if, for example, I want to get the area underneath that, I will be able to integrate this function, right? So how does this function look? The Dirac function, right, tau t, looks something like this. It reaches 1 over 2 taus, 1 over 2 taus, in between minus tau and tau, and it is 0 everywhere else. Does that make sense? I think so, because this is out of this range, it's 0. When I come to this range, it is 1 over 2 taus. So let's integrate this one with respect to time. Okay, so area underneath will be my integration. What is represented with the area underneath is what I'm looking for. Right away I can say that since this range is 2 taus, 2 tau times 1 over 2 tau is going to be 1. So this area is actually happening to be 1. Okay, that's good. And then to find that area underneath the curve properly, I'm going to define it from minus infinity to infinity. But when it's coming to the real, where the real data is, it's between minus tau and plus tau and 1 over 2 tau dt. If you do the operation, t comes out over 2 taus. If you put the ranges on, what I was saying before is true. 2 tau over 2 tau is gonna be 1. So regardless of which tau I choose, whichever tau I choose, the area underneath such a magical function is 1. That's a perfect thing, because I want my delta function to reach a 1 after integration too. So there might be some relationship between these two as well. Now, if I was to make this tau sized smaller and smaller and smaller and smaller, what's gonna happen? Because I'm independent of tau, it will give an area that is still 1. And on the limit, if that tau goes to 0, I would still have my integration defined, and in the limit it will go to 1. That's the beauty of it. Now I have created, look at this, I'm shrinking down the tau from a big tau 1 to tau 2 and a tau 3. So as I shrink them down, 1 over 2 tau 3, for example, rises up, because I need to make it still workable, okay, or reaching up to 1. So this means that as I squeeze in the range like this, as I squeeze the tau range, this function will shoot up, and at the limit it will go to infinity, but it doesn't matter. I'm interested in its integral, and the integral is independent of tau, and it's 1. That's the big thing that Dirac is telling us now. And if it's defined around 0, pushes it up to infinity. I show the infinity by an arrow here, but the area underneath that delta t function, which I'm now changing that naming of that function to d tau t to delta t, that's gonna be always 1. And let's see a time shifted version of that. Let's not look at 2 over here. A time shifted version will be delta t minus 2. It's going to be shifted by 2, let's say. This is the time shifted version, t minus 3. And if you want an area underneath that as 2, if you just want that, then you multiply it by 2, because that factor 2 will come out from the integration as it is, and it will become 2 times 1, and that will be it. So if you put an arrow that is 2 times the arrow that is 1 unity, that will represent a time shifted delta function by 2, which has a size 2. Okay, so this is how you solidify the abstract Dirac delta function from something that is going infinity to something that results in some solid number like 1 if you integrate it and take the area underneath that. So I hope this is clear. If not, just forget about it. So let's use it in a mechanical model, our famous spring mass model, right? If it's appearing like this too much in this course, you will see it in the rest of the courses quite a bit. That's an indicator. So now I have a mass. I'm pulling it, let's say, with force, and force is equal to ma. I have a spring constant that pulls it towards the wall with a minus ky, and I'm wondering about my position if I was to leave this thing in a one instant, or right now I will be interested more interesting stuff, like if I give a little push to that m in that linear directions, and bir fiske atmak. Okay, so we will do a little push to it, and what happens? That's with time. How does the displacement will change? That's something we're wondering about. Let's say in a vibration case, I'm wondering about how it will be damped or not. Now, the thing is, I can construct my equations. I'm pretty sure you're familiar with this now. My squared. I have the double prime is just y is my position. Okay, ky, and y double prime is my acceleration. My double prime plus ky is going to be the force. Now, if there is no outside force, meaning that F is equal to 0, spring starts moving on its own as I leave it. But let's say if I have some Dirac delta impulse, let's say at 2 seconds, okay, at time equals to 2 seconds, I have some sort of a delta Dirac impulse. So this is meaning that we push it a little bit, let's say, infinitely fastly at that instant of impulse. Now, Laplace of Dirac delta function is a time integral. Let's have a look at that. Yes, it's a time integral. Its units will be time, right? So if I multiply it by force to analyze my system, to make it like force, there will be still some time over here, time in due to the Dirac delta. So the left-hand side, let's say, is f times time. Let's make a unit analysis and see what's going on. And the right-hand side is, since f is ma, it will be multiplied by time 2. So if you sort out and put kilograms in mass, meter per second square for acceleration, and second for time, you will end up with kilogram meter per second, and that will be mass times velocity, which means that the impulse that I'm talking about in a kind of abstract way, is actually referring to a change in momentum. So, well, being infinite is then not that important. It's infinitely fast, yes, that I accept, but it changes the momentum of my mass in a very well defined way. Only when you take the time integral of such a delta function, that it becomes a well-defined momentum change. Why is that so? Because this delta function, when it's taken into a time integral, it will be leading to a well-defined momentum change if we analyze from the units that we will see. So what is that time integral? Let's think about that. Isn't Laplace is a nice time integral? Because if you remember the definition of Laplace, I have e to the minus st times my function, which is delta function now, dt, and I take the time integral of that. So let's do it. So if I take the Laplace of both sides, which I can do, I have my numerous exposures to ordinary differential equations where I take the Laplace of the outputs, and let's say this is my input. Yes, if you take the Laplace of that, that will become a time integral, and that's advantageous because something that is quite abstract, now within the integral, it becomes a well-defined momentum change, and within the integral, let's see what happens. So I have a time-shifted delta function. Let's say my impulse is happening right at c. I don't know why this doesn't come. Okay, right at c, and from minus infinity to infinity, whenever I hit c, the integral will become 1 because I have an impulse at time c. Now, if I have 2 times that, the area underneath will be 2, and I have something that is, if I'm looking at a different quantity, I'm just going to add this 2 over here. So the intensity of the impulse is 2, and I understand it from its area underneath. Okay. Only in the integral it becomes defined. That infinity becomes defined, and that is only possible, or maybe possible with different integrals, but Laplace integral will serve to make it solidified in our minds. And f of t, let's say I have some random f of t here, and in the Laplace integral, it needs to be multiplied by e to the minus st. That is our Laplace term. And if I multiply it by the delta Dirac function, which is shifted at c, then what's gonna and this is defined from 0 to infinity. So within the Laplace, our function starts from 0, goes to infinity, and let's say I have a multiplication of this Dirac delta with that function right at point c. Apart from that point, it's all the way from 1 to c, it's 0, or 0 to c, sorry, 0 to c, it's 0. So multiplication will yield 0. After c, it up to infinity, it's gonna be again 0. So multiplication of this function with 0 is gonna be 0. So only at that point where I put the impulse, it's going to be 1. And that, when it's multiplied by my function, it's going to turn to, I'm just going to plug in the point C. So e to the minus sc times f of c. That's it. That's my Laplace term, because it will simplify to 1 wherever I'm at C. It will simplify to 0 wherever I'm out of C. And this brings me a function that is just like a multiplier to my Dirac delta. When there is a multiplier, you can take it out, obviously. Sorry for that. And you can take it out as a factor. So it's just a multiplying factor that takes the intensity of my impulse up high. And so the Laplace of such an Dirac delta function times f of t, which is some sort of a force function, it's going to turn out to be f of c times e to the minus cs. Kind of like time shifted version factor coming from here, and the actual function evaluated at c here. Now, if it's just as it is, there's no time shift, c is 0, there is no the function is exactly 1, then e to the minus 0 s 0 s is going to be 1, and that's going to lead to just 1. So Laplace of Dirac function is just 1 on its own. If you shift it within time but leave the function as 1, then it's e to the minus sc. So let's see an example. This is the example 2 in section 6.3 on page 227. It's a hammer blow response of a mass spring system. So I'm going to give a unit impulse at time equals to 1, and that's going to be represented by Dirac t minus 1. And what's being given, the function is just 1 here, not to complicate things. On the left hand side, I have some sort of an output function that I need to reach the from which I can reach the original y function, which is going to be the output. The Laplace, if you take the Laplace of delta t minus 1, is just going to be e to the minus s, right? If I replace c by 1, it's going to be e to the minus s. Now, if you take the Laplace of the left-hand side, you can sort out the terms. Initial conditions are 0, so it's quite simple story here. I'm just gonna need to let me mark those for you. I'm gonna be leading these to 0. So what's left here? S squared, 3s, and 2 here. So those are my coefficients for the capital Y, and e to the minus s is on the right hand side. So now what happened here, I'm able to take the impulse function, put it in an integration like over here, okay, and that will now become a solid quantity, and it will be taken, when you take the Laplace of it, it will be reflected as a regular function that I can deal with it. I know how to deal with it, and turn it into if you want to take the inverse Laplace of that, it's now quite easy to take that. Now let's analyze this. I could do some little trick here. Probably this will do it. Why? Because s plus 2 minus s minus 1 is just going to give you a 1. So whatever that is over here in the parentheses is equivalent to here. And this is obviously an S shift. Okay, S shift. So an S shift is reflected to the time domain with the opposite sign, so it's going to be a minus 1 e to the minus t, a minus 2 e to the minus 2, and I have some sort of a time shift as minus 1 because I have e to the minus s over here. I have a unit function, obviously, that is representing a time domain shift. Now, the shift within the unit function is by minus 1, ut minus 1, and the original function was e to the minus t and e to the minus 2 t's, and those t's are shifted by 1. Okay, and that's like a piecewise representation up to 1. This will be, there will be no outputs. Okay, this is my output function. There will be no outputs after I punch it. Is that true? Yes, because everything is silent until 1 and I punch it, right? The mass spring system, I put a hammer to it right at 1. Until 1 it's silent, and after 1 it will something will happen. And what will happen to a spring? Actually, it will damp because of, let's say, if it's in air, the air molecules, and it will slow down, and it's an exponential slowdown with this strange function because of my constraints given in the original output functions. Okay, now this is about it, about the drag function for now. And let's move on to section 6.5, convolution integral. Let me see if I have something here. I think, yeah, why do we need something called convolution, Laplace convolution theorem? Convolution has to do with the multiplication of transforms. If you remember, just a moment ago, we had something appearing in the right-hand side, in the frequency domain, that can be represented as multiplications. Whatever we do throughout the whole Laplace course that we have been presenting, we were doing, I'm not sure why it doesn't come. Okay. We were doing something like this, right? Partial fraction expansion. Why? Because I had two multiplications here which were critical. I could not decompose or understand them in terms of multiplications. I tried to put them in a format where I can recognize the functions in the addition or subtraction format, right? So in those situations, I needed partial fraction expansion or some clever ideas to make this happen. Okay, if you watch some videos that I will be giving you, you will see some of those approaches, or something like this. I put minus plus, or I dissociate the 2 into 2 so that I can write this in a clever way to get the solution quickly. So that's always possible. But if you cannot, that's a big but there. Sorry for this is taking too long. Okay, the computer is I hope it will not crash. So let's see if we go to our example here. The most recent example, we had something like this. We used our intuition that, okay, if I put that here, put that there, since these are quite simple expressions, I can probably sort it out without using partial fraction expansion. But in some complicated situations, you might need a convolution integral. Why? Because although you can separate the addition of the transforms is straightforward, linear. So if you have addition of two functions, it just reflects as Laplace of both of them separately. But when you multiply two functions, it doesn't correspond to the Laplace, or if you have the Laplace of two separate functions multiplied together, it doesn't equate to the Laplace of multiplications. Let me go back to these notes here very fastly. We need something interesting here. It's like this actually. It's like defining a new rule for some operation. Let's say I have a and b equals to a plus b. If I define this operation as summation, you would be okay. Yes, whenever I see this circle, I put a plus sign there. Actually, what convolution is, let's say it's a triangle operation, and something that you haven't seen until now. It's a star operation. We will show that by a star. It could have been doing something like this. A plus b squared over 2 is equivalent to, let's say, a triangle b. So this could be the rule of triangle operation. Well, I'm just going to define it for myself, and actually we're not going to prove the theorem, but convolution is the solution for that problem. So let's see the problem for ourselves. Let's say f and g are two functions, and I take Laplace of them separately. Is it equal to their multiplications and then taking the Laplace of them? Well, it will not be for most cases. Say f is e to the power t and g is 1. Fg is e to the power t. Laplace of fg is 1 over s minus 1. Now, if you look at Laplace of f, it's also 1 over s minus 1. But Laplace of 1 is going to be 1 over s. So the multiplication of the individual Laplaces will lead to 1 over s squared minus s. And it's not obviously equal to 1 over s minus 1. So multiplication is rather a problem. And whenever a situation like this comes up, I need to put that into a summation form for reaching my output functions over here. But we could do a little trick or use this convolution property and define a new operation that is shown by star, and that star is convolution. Convolution of f and g together is going to be called, let's say, ht, and it's like looking like an integral like this, f tau. So some variable, like if I'm going to take it with respect to d tau, the same variable in one of the equations, expressions, and t minus tau in the second expression. So basically it's some sort of an integral operation, whatever that convolution is, the star operation. It's an integral operation, and in which I have one of the functions expressed in terms of tau, the other one is somewhat shifted by tau. Okay, so this is, I'm not going to go into those details, but you can see the examples in your book. So f convoluted to g is going to be ht, and if you take the Laplace of both sides, then hs is going to be the Laplace of h, and Laplace of f convoluted g is going to be Laplace of f times Laplace of g, so f of s times gs. So whenever I see a multiplication, if I do want to go back to back to the time domain. From there, I can instead of using multiplication in the time domain, I need to use convolution. Okay, put them in. You want to use, yeah. Okay, so whatever I'm saying is written in a proper form there. Let's read it out. So instead of partial fraction decomposition to put them into summation, if you want to use the HS in its multiplication form, you need to express it as convolution of two functions in the time domain. So let's say I have an HS looking like this. I need to rewrite this in a way that it is the product of two Laplace transforms that I know. Because if I take the inverse Laplace of that, I can convolute them. But how does it look? So let's see HS, 2s over s squared plus 1 squared. So maybe if I just separate it out like 2 over s squared plus 1 times s over s squared plus 1, I now have something sensible, because if I was to take the inverse of this one, this will be 2 sine t's. If I was to take inverse of this one, it will be cosine t. So literally, these are something that I know. I'm familiar with it. I know the Laplace transformation of those. So in the S domain, if they're multiplied, they need to be convoluted in the time domain. So inverse Laplace of this first term, Fs, and inverse Laplace of this second term, G of S, needs to be convoluted in the time domain. So this is exactly 2 sine theta convolution to cosine t. Now, if I use my theorem from the book, f convoluted to g is 0 to t, f t minus, well, it's a little bit different from here maybe, but don't worry about it. It's just the same thing. You pick up one of the functions, that's what it is. You pick up one of the functions, express it in terms of t minus tau, and you pick up the other function and express it as it is as g tau and do the integration. So for our case, for our simple example over here, for hs being equal to this, our solution will be 2 sine theta convoluted to cosine theta. Those are my f and g's. And 2 sine, let's pick up the first equation, so expression, 2 sine t minus tau, that's good, and cosine tau, that's good. So if I was to do this integration, which is doable, I promise you, if you can do it in 10 steps. I did that and it took about 10 steps if I'm not mistaken. And you can reach some expression like 2 is from outside, okay? You can pick that 2 out. 2 times 1 over 2 sine t, t sine t. So this means that sine t, if you exclude that 2 here, sine t cosine t, if you convolute them, 1 over 2 t sine t. So you can have some tables of these as well. That's a good thing. And convolution tables will lead you to some of the solutions with an easy one-step thing, because if you can find a table that does that integration for you, you will reach the 1 over t sine t right away, and then that will correspond to, for our specific problem, t sine t. Okay. For another example, please have a look at Dr. Bulge's lecture notes. I will distribute these notes. There are some solved examples in them. So you will have this week some video files on YouTube, and then the normal regular PowerPoint file. And then addition to those two, I will have some lecture notes for solved problems from Dr. Bolger. Okay, now let's move back to whatever left in the course. Okay, I have a number of slides, but they're not gonna take too much time. So we solved this. Did we solve this? Yeah. Okay. In Bulge's notes, the example solved with the convolution is this one. So how do I take the inverse Laplace transform of such an expression? I need to really do fractionate this one into two, and then without applying the partial fraction expansion, I'm just gonna go with the convolution to solve this problem. And that's what's done in Dr. Bulge's lecture notes. Section 6.6 is not included. Section 6.7, a system of ODEs. Okay, so let's say I have the first equation going like that. I have an input. I have my kind of, well, these could be taken to the left hand side, so there's no problem with that. So my input will be on the right hand side, and all the output related stuff, the y related stuff, will be on the left hand side. But for some ease, for first order equations, the expression, putting them into an expression like this will be easier. Actually, you probably had done this in eigenvalue problems in ODEs before. If you put it in this form and take the Laplace of everything and define Laplace of y1 as capital Y1, y2 as capital Y2, and so on and so forth, you can reach up to some expressions like this. The left hand side is obviously sy capital Y1 minus y1 at 0 and y2 at 0, and the left hand side is pretty obvious. Right hand side is just taken the Laplace of all those functions. They are capitalized. Now if you sort the terms out and try to reach some sort of an expression or set of equations where you actually you have all the capital Y terms on the left hand side, capital Y terms on the left hand side, and the initial conditions and the input on the right hand side, then you can solve this algebraically. Okay, you can. I'm not gonna give a perfect example. I have something here, but the real solution will be in the lecture notes that we will be distributing. But what we have here is a linear set of equations. How can you solve them? By using, let's say, Cramer's rule, right? Example 1 in the book, this is on page 242, the mixing problem involving two tanks. I have salty water in one of them and plain water in another one of them, and there's a little circulation between the two tanks over here, and I have a constant supply of another salty water coming from here, and a constant exit from there. So I wonder about how much time it will take for this to equilibrate once I switch on, okay, these two tanks. And after some point, I want these two tanks to be in a steady state such that they would supply a constant salty water. But before that, it doesn't happen to be like that. Let's say this is like some sort of a environmental system that one company uses. So before switching it on, the salt concentrations in the tanks are not equal. But once I switch it on, it takes a certain amount of time to reach a steady state salt concentration in the outlet. Okay, so you can, I think you have modeled this in your previous um, course. So because it's on page 14, the real modeling that you see here in terms of those differential equations is appearing at on page 14 as well. Okay, so please remind yourselves that this is one story. The mathematics is united, so it's not a separate thing. It's the same thing that you can solve in another way. Uh, so you can all, I'm not going to literally spell out every step, but obviously these equations, when you take the Laplace of them, Laplace of 6 is minus 6 over s. Maybe it's not minus, but it's 6 over s. But when you shuffle the equations, it becomes that. And so if you take the inverse Laplace, so let's put out this one here first. If you solve this equation by Cramer's rule, which you can do, you can find an expression for y1 and y2. Okay, that's something you need to do on your own because you know linear algebra and you know how to solve such equations with different methods. You can eliminate, you can use elimination too. In any case, you can reach for y1 some expression like this and another expression like that. Then there's a tedious job. It's not like one line here. To reach from these expressions, the raw form, ham hali, raw form of these expressions to the like fine-tuned versions, you need many steps of partial fraction decomposition. You could do deconvolution too, but that's not going to be easy too. Deconvolution or partial fraction decomposition, you reach these. Okay, and that's something you need to do maybe with a computer. You can use MATLAB to do partial fraction decomposition actually, and that will give you that. And if you take the inverse transform, you will end up with some nice equations because these are like some shifts in the frequency domain that reflects back as an exponential here. And that's it, right? So you have a normal plane function there, and those are like the target values probably. Target value is going to be like 100. And these will be the kind of um, how you approach to that target in different tanks. Okay, and these are going to be some exponential terms, and if you plot them out, you would see that the salt content in tank 2 was originally 150. It will drop down sharply, and then it will elevate back to the target level after some seconds, if this is in terms of seconds, for example. And if you look at the tank 1, it's steadily gonna increase to the steady state point. You can use some MATLAB codes. They are all discussed in that sheet that we will be distributing. So thanks to Dr. Balger, he did all that coding and generated the same results in the MATLAB. You can have a look at those codes too. So there are some examples with discontinuous forcing functions like heaviside step function or ramping function. That's something I haven't mentioned in the lecture notes over here. So you can have a look at these. For example, a kind of a step function that looks a little bit more different than what we have been seeing until now, or a ramp function. Okay, have a look at this, how it works. You should make yourself acquainted with that because you will see ramp functions in your control classes. An LC circuit, an example for that, an example for an RC circuit, how you can use all these unit step functions there in initial value problems. Okay, you can look at those on your own. And then a mass spring damper system, as shown, will be investigated. There, there we will have four different functions, input functions. One is going to be an impulse function, delta drag. Another one is going to be a unit step function, UST, and a ramp function. Okay, those are the two functions that you know. Another ramp function that you will learn from pages before, and then a sinusoidal function. Okay, we will look at all these initial inputs, and then the outputs will be some response of those systems to impulse unit, or a ramp, or a sinusoidal function. So these are all the things that you will learn from those notes that I have prepared by Dr. Balji. Now, I want to talk a couple of minutes for as a conclusion for Laplace transform. Uh, we have now the fundamentals of Laplace transform. It goes deeper, obviously. It's 2 weeks is not enough to cover all these, and since it's online, we have much less interaction here, so it's difficult, I know, but I think it's manageable. Huh? So the way we describe it is quite a simpler version of what it could be. But later you will see more of the transfer functions. You will add something called block diagrams in your control classes. But before moving on to that, there are literally tons of YouTube videos on Laplace transform. Maybe this is not the best, okay? This is probably not the best, but it it has such a systematic way of describing the stuff related to control. It's it could be a link between this course and the other courses and the other videos that you might encounter in the internet. Okay, so let this be your starting point. It's like just a 6 episode, like each one is 15 to 20 minutes, and it's describing a very regular method. It's repeating itself and so on and so forth, but it puts you in a good position with respect to your control classes. I believe that might help you. And final words, please go back to your differential equation course notes. You will see, and it will reflect more after taking this course. And modeling a physical or chemical phenomena, these are the stuff that you learned already. Go back to those material in your previous notes, and with this refreshed and diversified background, now you're able to read math, listen to math, watch mathematics videos with more ease. I think that will be the thing that this course tries to do. Hopefully, these videos were somewhat useful for you, and I wish the best of luck in your finals. And we will see you in the department once this pandemic passes over. Okay, good luck.